So up till now, what we have seen, we have understood what is forward difference, what is backward difference, and what is central difference. And we have seen the operators for forward differences, backward differences, and central differences. Now what we'll do, we'll understand these operators in a better way. Before entering into, before exploring interpolation, we'll understand these operators first. We know what is this. This is the forward operator, or it is called descending operator also. So if we say del of fa, if fa is a function, f is a function, then del of fa, the meaning is fa plus h minus fa. Clear? In the table, this minus this was the meaning of this del fa, the first difference. We can write fa plus h, the second difference, as fa plus 2h minus fa plus h. Clear? I am just giving you a revision of what we have already learned. Similarly, del of fa plus 2h is equal to f of a plus 3h minus f of a plus 2h. This we know, this goes on. If this is a plus nh, this will be a plus n plus 1h by f a plus nh. So this is the forward operator. Now the second degree operator, that is del 2. On similar terms, this was del of fa plus h minus del of fa. Clear? This is this, then this is del of this. We can write this as, from here, this is del fa, and del fa plus h was, this was a plus 2h minus fa plus h. This and this is minus fa plus h minus minus plus fa. So actually what we get, this is f a plus 2h minus 2fa plus h plus fa. Clear? Similarly, we can go for del 3fa. See, the third degree operator. What this will be? This will be del 2 of this minus del 2 of this. And you can take a value like del 2 fa is this. Similarly, you can find value for this and this. You don't have to learn this. You have to understand this, how the operator works. So this is essentially a revision of the concept that you have already done. What we actually want to achieve, you can ask me why we are learning these things. We can, tabulate and get these values. When we have values, we can tabulate and get different, first, second, third differences. But what if we have equations, we have functions, and from functions we have to find the third, if we have been given a function fx and we want to know what is del 3fx, or we have been given with del 3fx and we want to know what is fx, then how can we, from the third operator of fx, how can we get back to the original function fx? That is what we actually want to achieve now. So up till now, I think things are clear to you. This is not difficult. Just brush it up so that when we proceed, you don't get confused. So what we saw was that if we take the nth, this derivative, or you can say the nth operator, the nth power of this forward operator of f of a, what we actually do is n minus 1 of a plus h minus n minus 1 of fa. This is what we were doing in generalized terms. Okay, you should keep this expression in mind. There is nothing to call it a formula. It is just an expression. Now there is a very important theorem here. The theorem says that if we have equal spaced intervals, that is h, we are using a, then a plus h, or we were using x0 plus h, x0 plus 2h, that is, the differences are equally spaced. So in this case, when the differences are equally spaced, then for a polynomial of nth degree, what is polynomial of nth degree? This is axn plus b xn minus 1, and it keeps on decreasing. Let's say m x and then finally a constant. So if we have a polynomial of nth degree, then the nth difference operator, the nth difference will be a constant. That is, if we take the nth difference of this function, this will be a constant. This is theorem, and it is a very important theorem. And from here only you can understand that if in that table, that is column 1, column 2, first difference, second difference, it comes to the nth column, and if all are constant k, then all n plus 1th columns, the values will be 0. All other differences will be 0. That is, all the differences above this column or above this degree will be 0. And the converse is also true. That is, if you make a table and you find that in the fourth column, that is the fourth difference, we have all the same constants, it means that the function for which this table has been tabulated is of degree 4. Clear? Again I am explaining. For equally spaced intervals, this is the first condition. Equally spaced. Not for a plus h, a plus 5h, a plus 7h, no. If this is a plus h, a plus 2h, a plus 3h, so if we have function and we have equally spaced differences, then for a polynomial of nth degree, the nth difference will be a constant, and so all the differences above this nth column will be 0. And the converse is also true. That is, if the nth column of a table is all the differences are constant, then we can say that the polynomial, the function for which this table has been constructed, is of nth degree. Clear? And there is a derivation. I am not going into the derivation because that is not required for this course, but the result is very important, that del n of fx is effectively del n of this particular part, the first term of the polynomial, and it actually comes to a, the first term, into h, that is the interval, and into factorial n, that is this n, the nth part. So this is a constant. You can see this is coefficient of x to the power n, this is the interval, and this is factorial n. If we have to find del 3, this is factorial 3, for 4 factorial 4. So this is a very important result that you should keep in mind. Clear? That the nth difference of a function is actually the nth difference of the first term, which is ah factorial n. We have seen in the theorem only that if the polynomial is of nth degree, the nth difference will be a constant. Clear? Keep this in mind, ah factorial n. Now let's see an example to understand this. Let our function be 1 minus x into 1 minus 2x into 1 minus 3x. Okay. Let the interval h be equal to 1. What we have to find is, this is nth degree, this is third degree. See, cubic equation. So let's find what is del 3 fx. It has to be a constant. We know this. How can we find? In the last slide only, I had told you this is a into h into factorial n. So in this case, we'll see what a is. So a into h is 1 and factorial 3. So let's find what is a and we'll get the answer. See, let's expand this function. This is 1 minus x into 1 minus, see, 1 minus 3x minus 2x. So minus 5x plus 6x square. So this is 1 minus 5x plus 6x square minus x minus plus 5x square, and this is minus 6x cube. So the highest power, whatever this be, this is the highest power. So a is minus 6 here. So what do we get? Minus 6 into factorial 3, that is 3 into 2. So 6 into 6, 36. So del 3 of fx is minus 36. That is, if you have this function and you tabulate it in the forward difference table, what you will get? In the third column, the third difference column, you will get all the terms equal to minus 36. Okay. Let's say we have to find this del n, and the function is e ax plus b. So we have to find this given h is equal to 1 and a and b are constants. Okay, we have to find this term. How we can find this? What we'll do, we'll get the answer by mathematical induction. See, first del of e to the power ax plus b. What it is? You have seen it is actually fx plus h. H is 1, so we can say x plus 1 minus fx. This is the meaning of del. So function of x plus 1. So this is a into x plus 1 plus b minus e to the power ax plus b. What this will be? This will be e, see, a plus ax plus b minus e ax plus b. So we can write e to the power a into e to the power ax plus b minus e to the power ax plus b, or we can say this is e to the power a minus 1 into e to the power ax plus b. So this is first one, del of this. Okay, I'm writing it here. Del of the function is e to the power a minus 1 into the function. Okay, now let's see del 2 of this. What is it? It will be del of e to the power, what do we do? X plus 1. When we have to take del 2, it means del of, see, like this, fx plus 1 minus del of fx. Clear? So, and what is this? Del of x plus 1? This will be fx plus 2 minus fx plus 1. And what is this? This will be fx plus 1 minus this. We had done this. So this will be minus fx plus 1 plus fx. Okay. So effectively what we get? We get fx plus 2 minus 2 fx plus 1 plus fx. Okay. So let's put the value here. This will be e to the power ax plus 2 plus b minus 2 e to the power ax plus 1 in plus b plus the function ax plus b. Okay, correct? X plus 2, twice of 1 and this. Okay, so what do we get? E to the power 2a will be out of here, or this term, and we'll get ax plus b, the normal function. Then here 2 e to the power a out, then e to the power ax plus b, and finally this is e to the power ax plus b. Okay, so what this is? This is e to the power 2a minus 2 e to the power a plus 1 into e to the power ax plus b. Clear? What is this? This is e to the power a minus 1 square. See, this is square, so this is e to a plus this square. 1 minus 2 into this. So this is EA minus 1 square into e to the power ax plus b. So what do we see? The first function was EA minus 1 into the function. This is EA minus 1 square. Therefore, del 3 will be EA minus 1 cube into this. Del 4 will be EA minus 1 4 into this. That is to say, if we go on like this, del n of this function will be nothing but EA to the power EA minus 1 to the power n into the function, that is EA x plus b. Clear? This is our result. This we have got by mathematical induction. Okay.